I'm Julia.
I'm Elizabeth.
I'm Macy.
I'm Katie.
And I'm McKenna.
And this is
Absenteeism at Work! The business problem we are evaluating is what factors are related to employees being absent from work. The measures are age, number of children, education level, distance from residence to work, season, social smoking, social drinking, and BMI. Our data source is UCI Machine Learning Repository, and our data set is Absenteeism at Work. Our method and tools are multi-collinearity tests followed by regression modeling, pivot tables for graphs, interpreting data analyses in correct context, and answering analytical questions. Our conclusion is significant factors in predicting absences are age, distance from residence to work, BMI, and social drinking. Our motivation and context. Our motivation is determined factors related to employees' absences. We're trying to figure out what makes employees absent. We're informing employers of results to determine if they can institute preventive measures or if it is out of their control. So ultimately, our context is dealing with how much absenteeism is a bottom line killer. Absenteeism is incredibly expensive for workers. As you can see here, it costs workers roughly $3,600 a year per hourly worker and $2,650 a year per salaried employee. And the annual implications start to add up nationwide. The annual cost of loss of productivity due to health is about $84 billion. The costs vary by industry, but the greatest losses occur in professional occupations. The business problem that we are trying to answer is that employers are curious to understand what factors play into absenteeism in the workplace in hopes to reduce unnecessary absenteeism. Our questions are, do specific age groups have the more total hours absent from work? Do social drinking account for a significant amount of absenteeism in hours? Is there a positive linear correlation between BMI and total hours absent from work?
We're making a few assumptions about our data. One is that proper data collection techniques were used in gathering it. Another is that our conclusions will help predict the factors that are most or least likely to cause absences. We're also assuming that these conclusions will be applicable to other businesses in other countries. We're also assuming that the characteristics of lifestyle, life cycles, time frame, and health are critical factors in predicting these absences. Finally, we're assuming that the data accurately depicts absenteeism causes in a company. We gathered our data from the UCI Learning Repository team consisting of David Aha and his graduate students. The data is about employee absences that occurred at a courier company in Brazil between July 2007 and 2010. Within the data, there are 741 rows and 20 columns, of which we only utilized a few, being absent time and hours, education level, social drinking, age, distance from home to work, body mass index, number of children, social smoking, and season. To define these variables, we created this chart. For absenteeism time, we are looking at that in terms of hours per day per absence over the 3 years the data was collected. For distance from work, it was measured in kilometers. The column sun was actually determined to be the number of children. For education level, it was collected over the education levels of high school, graduate, postgraduate, and master's and doctorate. For social drinker, the dataset created dummy variables consisting of 1 meaning yes and 0 meaning no. The same was done for social smokers. And the BMI is defined as the body mass index, which is a measure of body fat. For seasons, the data also represented the variables in numbers consisting of summer, autumn, winter, and spring.
Okay. We conducted a multiple regression model, and there we found that there was multi-collinearity within some of the variables. From there, we tested the strong correlation between the independent variables and took out the ones that were greater than 0.7. After we did that, we ran our multiple regression again and found that our p-values that were higher than 0.1 we excluded from the model. When running our multiple linear regression, we had found that there were values with high p-values that meant that they were not significant to our data set. They were spring, postgraduate, autumn, graduate, high school, summer, social smoker, number of children squared, and winter.
The variables we found significant: distance from residence to work, age squared, social drinker, and BMI. Through regression, we eliminated all variables with a p-value lower than 0.1.
Go.
We first tested for multicollinearity among the independent variables and excluded variables that had a value greater than 0.7. We then looked at the relationships and found that the independent and dependent variables are linear. And we also looked at the regressions of the independent variables for any that had a U-shape, and the ones that did have a U-shape, we used a quadratic method and squared their terms to make the scatter in them random. Our data did meet the central limit theorem because we have 740 rows, which is greater than 30. The two methods we decided not to use with our data were hypothesis testing and chi-square testing. We decided not to use hypothesis testing because we decided that our data was not a sample of the entire population, but only a sample of one company. We did not use chi-square because our independent variables were not due to chance and they fit the data. The forecasts we used were historical average and exponential smoothing. We decided that historical average was the better method because it had a lower MSE between the two.
Go.
Before running our regression, we decided to make a correlation matrix to test for multicollinearity among our independent variables. We removed variables from our regression that had values over 0.7. For example, this one and this one.
First, we conducted a single linear regression model for these independent variables. Age squared, BMI, distance, and social drinker. We found very low R-squared values, and then we moved into a multiple linear regression, which we'll discuss next. After we ran our multiple linear regression model, this was the equation we had come to. The independent variables for them are in this order: distance from residence to work, age squared, social drinker, and BMI. Our statistical analysis concluded that all of the p-values for these respective independent variables were lower than our significance level of 0.1. Therefore, we included all of these in our final regression model. When running our regression, we had found that there was a quadratic relationship between age. Therefore, we squared it and put it into our equation, and that's why age squared is in our equation. This is the pattern that we had seen earlier and why we chose to square age for our linear regression model.
This is our residual plot for age, and as you can see, there is a U-shape. Because our residual plot for age had a U-shape, we decided to square it, and as you can see, our age squared plot still has a U-shape, and we decided to keep it because the p-value was significant. This is our BMI residual plot, and as you can see, there is no quadratic relationship. Our distance from residence to work residual plot also had no quadratic relationship. The data presented social drinker as a dummy variable, and that is why it can only be presented as 1 or 0. And that's why our residual plot looks like this. We created a pivot table using age groups and hours absent. Using the pivot table, we created a line graph that shows a negative linear correlation between these variables. We created a pivot table using the social drinker dummy variables and hours absent. Using the pivot table, we created a bar graph that shows a positive linear correlation when people are social drinkers. We created another pivot table of employees' BMIs and the hours they were absent. Using the pivot table, we created a line graph that shows a negative linear correlation between these variables. People working in a courier job where we got the data from are generally required to be in good shape because of the strenuous activities they may be required to perform on the job, which has likely skewed the data.
Our conclusion is that the independent variables that were significant were age squared, BMI, distance from residence to work, and social drinker. Here's our predicted absenteeism equation. The p-values for social drinker and h squared had the largest impact on absenteeism overall. To carry on our conclusion, we asked the question, what factors are related to employees being absent from work? We found that distance from residence to work, age, h squared, social drinker, and BMI had the largest impact from employees being absent.